Hello students, welcome to 60 out of 60 in KCET Chemistry in 2025 in just 200 days. So as you all know, revision is the key for retention, and for organic chemistry it is very important to revise the chapters regularly. Okay, so in our series we have just completed Haloalkanes and Haloarenes chapter. So in today's video we are going to revise this chapter. Okay, so I'll be teaching you how to draw the mind maps, okay, how to write all the reactions in one single page and how to revise it. So yes, let's get started. Very important. So this will be like a one shot of your haloalkanes and haloarenes. So everything that is asked in the exam will be covered in this video. Okay, so yes, now without any delay I want all of you to sit with a pen and a paper and your notebook and to draw the mind maps effectively, to learn how to draw the mind map so that you can use it for other chapters also. Okay, so yes, now let's get started. So the first one is like, how are we going to cover this chapter? So this I have discussed many times. So in the first part we have okay, so now if you see, we have that first we will be talking about classification, nomenclature and nature of CX bond. So this we will do little fast. These three are important: preparation of haloalkanes, haloarenes and physical properties, and main focus will be doing about the chemical reactions. Okay, so yes, now coming to the year wise weightage. So every year like 2 to 3 questions you can expect from this chapter. So now coming to the part 1, that is your classification, nomenclature and structure of CX bond. Okay, so these three things we are going to discuss. Okay, now under classification, see, there are three bases on which the compounds are classified. First is number of halogen atoms, second sp3-CX bond. Okay, so this based on this CX bond where this C has to be sp3 hybridized, on that we have some classification. Next we have sp2-CX bond, means this one, sorry, the sp2-CX bond, like the classification here, CX bond is there, but this carbon is sp2 hybridized. sp2 hybridized means it is bonded to another, it's a double bonded carbon. So classification for this one and this one also we are going to check. Okay, fine. Now coming to number of halogen atoms. So based on, if there is one halogen atom we call it mono, if it is 2 di, if it is 3 it is tri. In the haloarenes, if there is 1 then it is monohaloarene, 2 then we call di, and if we have 3 we call it trihaloarenes, right? Okay, next coming to the classification of sp3 carbon. So what I told you, that there will be carbon hydrogen X bond and this carbon is sp3 hybridized. Okay, now if you see in alkyl halides, okay, in alkyl halides we have three types of first category in alkyl halides. See, the carbon which contains the halogen, if it is attached to only one carbon then we call it primary. If the carbon which contains the halogen is attached to 2 carbons, we call it secondary. Now if the carbon which contains the halogen is attached to 3 carbon, then we call it tertiary, right? Okay. Now coming to allylic halides. In allylic halides, see what is the scene, that the carbon here you see, this is the carbon which is containing the X or which is containing the halogen. This carbon should be attached to a double bonded carbon. Okay, this carbon should be attached to a double bonded carbon, then we call this halide as allylic halides. Okay, carbon which contains the X should be attached to a double bonded carbon. Okay, now benzylic halides. So benzylic halides is like this: the carbon which contains the halide should be attached to a benzene ring. Okay, should be attached to a benzene ring. Carbon which contains the X group should be attached to a benzene ring. Now carbon which contains the X should be attached to a sp2 carbon or a double bonded carbon, that is your allylic. Carbon which contains the X should be attached to a benzene ring, that is your benzylic carbon cations, benzylic haloalkanes. Okay, next coming to your sp2 carbon. So that means here what is the structure? Carbon is there, X is there, and this carbon is attached to, and this carbon is sp2 carbon. Okay, so in this case we call it, if the X is directly attached to the sp2 carbon, we call it vinylic. Okay, we call it vinyl halides. Okay, here you can see this X, okay, which is directly attached, that is called as vinyl. Okay, now there is something called as aryl halide. So this one can, like, if there is if this X is attached to an aromatic ring, we call it aryl halides. Okay, X attached to aromatic rings is called as aryl halides. X attached to any double bonded carbon, sp2 carbon, is called as vinyl halides. Okay, so now let us quickly revise the classification. First one is on the basis of numbers, that is very easy by saying 1, 2, 3, mono, di, tri. Now coming to sp3 carbon, the X, the halogen is attached to sp3 carbon. Here the first one is primary, secondary and tertiary. Now the carbon which contains the X group is attached to a sp2 carbon, or the carbon which contains the X group is attached to a double bonded carbon, then we call it as allylic. And if the carbon which contains the X group is attached to a benzene ring, we call it benzylic. Okay. Now coming to sp2 carbon, if the carbon sp2 carbon is directly holding the X bond, we call it vinyl. If the carbon is the X is attached to a benzene ring, we call it aryl. Okay, I hope this classification is clear. Okay, now let us solve which of the following is a tertiary alkyl halide. So tertiary means what? If you have remembered, tertiary means C should be there and this carbon should be attached to 3 other carbons. Okay, then we call it as tertiary. Okay, so now if you see here, this one, this carbon, if I see, we have like this C, C, and then we have Cl, and this side it is 2C. Right. So this carbon which contains the halogens is attached to 3 carbons, right? So definitely this is my answer, which is a tertiary tertiary haloalkanes. Okay. Next, coming to nomenclature. So nomenclature is very simple here. Just you have to use the word chloride, bromide, or like in the common name. So the most important here is common name. You should know the structure of secondary butyl, neopentyl, tert butyl. Okay, vinyl chloride, allyl bromide, and then benzyl chloride. Okay, so these 5 common names are most time it is repeated. So your this one, first one, sec butyl chloride is like this. Okay, so see, now this is a secondary carbon, so we call it sec butyl chloride, or its IUPAC name will be 2-chlorobutane. Now if you say neopentyl, it is like this. Okay, if I draw like this, okay, so CH3 whole 3 C, and then we have CH2Br, right? So if it is 1 bromo 2,2-dimethyl propane. So if this is there, this is called as neopentyl bromide. Okay. Next, one thing I have left, I think there is 3 CH3, 1, 2, 3, then this is 4. And then this is 5. Okay, 5 carbons are there, that is correct. Next, tert butyl means we have like this. Okay, so in tert butyl the parent chain is there, so 2 bromo 2 methyl propane. Okay, next vinyl chloride as I told you, the chlorine should be attached to the double bonded carbon, right? So that is called vinyl chloride. Now allyl chloride, we have allyl chloride like this. Okay, carbon should be attached to the allylic carbon. Okay. So other names are very easy, you should remember some more. Chloroform, CHCl3, okay, CHCl3 is chloroform, CHBr3 is bromoform, okay, and benzyl chloride is benzene with CH2Cl, and its IUPAC name is chlorophenyl methane. Okay. Next, okay, any other CCl4, carbon tetrachloride or tetrachloromethane, these are all easy things. So now coming to some question here. Okay. So now see the first question here, the correct IUPAC name of the compound. Okay, so for nomenclature you should know a basic rule that when the substituents are given, okay, the addition of the position of the substituent should be a least number. So if you see now, add 4, 5, 6, 7, okay, I'll get 7 here. Here 4, 3, 7 plus 1, 8. Okay, here 6 plus 3, 9, and then it is 1 nitro, so 6 plus 3, 9 plus 1, 10. Here I'll get 5, 6, 7 plus 1, 1 nitro, 5, 6, 7, 8. Okay, so the least number is given here, so this has to be the correct order or correct order of numbering. Okay, next, now nature of CX bond. So what is the nature of CX bond? If you have C and X, X is electronegative, so this is delta minus and this is delta plus, right? So here I can then say that the CX bond is slightly polar in nature. Okay, fine. So now coming to another question, the compound having the longest CCl bond. So CCl bond will be longest if it is a purely single bond. Okay, if there is any resonance, then they will have a partial double bond character and the bond length will decrease. So now if we see these options, okay, here there is a partial double bond character because of resonance, here there is a partial double bond character, here also there is a partial double bond character. So now if you see, these are where there is a pure single bond, so this is the longest one, or we can say that the correct answer for this question is option number B. Okay. So now we'll go to the part 2, that is your preparation. So preparation of haloalkanes, preparation of haloarenes and their physical properties. So if you see preparation of haloalkanes, we have 3 different methods. Okay. So first one is from alcohols, second one is from hydrocarbons, and then that is your halogen exchange method. So from alcohols we'll study, from hydrocarbons again we have from alkanes and we have from alkenes. Okay. Next, in halogen exchange method we have Finkelstein reaction and we have Schwarz reaction. Okay. So we will do all this revision of these reactions. So under alkenes we have again addition of HX and addition of X2. Okay. Fine. So let us start. First one is from alcohols. So you have to take ROH, okay, and if you take HCl and ZnCl2, okay, HCl and ZnCl2 will give you RCl. If you want RBr, you can take NaBr and H2SO4. Now you can take PX3 also to get RCl or RBr. PCl5, you should remember RCl plus POCl3 plus HCl. For these two reactions, please remember the byproducts also, RX plus H3PO3, here RCl plus POCl3 plus HCl. Okay. Now red phosphorus, here you can use bromine and iodine to get RX. SOCl2 will give you RCl plus SO2 plus HCl, and this you have to remember, this is the more preferred method. Why? Because the byproducts produced here are in the gaseous state. Okay. Fine. Next, coming to from alkanes. So from alkanes, that is a free radical halogenation. So just take chlorine in presence of light. All these halogens will be, all these hydrogens will be replaced with chlorine. Now here one problem is that we get a mixture of products here. Okay. Now these mixture of products are there, so it is very difficult to separate them. Okay. Next one is from alkenes. So alkenes means what? We have double bond. Okay. So if you add HX, okay, addition of HX, it will follow Markovnikov's rule. What is Markovnikov's rule say? The X will go to the carbon having less hydrogen. Okay. So if there are 2 carbons here, you can see this carbon is having 1 hydrogen, this carbon is having 2 hydrogen. So X will go to the carbon having 1 hydrogen. Okay. The less number of hydrogen. So this is the addition of HX and then addition of X2. So double bond will break and we will get 2X attached here. Clear? Okay. Next, coming to halogen exchange method. So first one is your Finkelstein reaction. So in Finkelstein reaction, what happens? It is used for the preparation of iodoalkanes. Okay, iodoalkanes. Okay, so RX plus NaI in dry acetone will give you Ri. So this I will come here and this X will come here. So we'll get Ri plus NaX. Okay, then Schwarz reaction is for the preparation of fluoroalkanes. Okay, for the preparation of fluoroalkanes. So now if you see Rx and different metal fluorides we can use. What you can use? Metal fluorides. Okay. So what are the different metal fluorides we can use? AgF, Hg2F2, COF2, SbF3. So these all can be used to give you Rf. Okay. So yes, now with this, preparation of haloalkanes is done. Okay. So now we will do a mind map for this. I want all of you to draw with me, where we are going to do all these reactions that we have studied in this one particular diagram. Okay. So that is very important. So I'll tell you how to do. So first, what are we going to prepare? That should be at the center, right? So we are going to prepare haloalkanes. Haloalkanes, or I can write it as Rx. Okay. Now what are the different sources? First one we have studied is from alcohols. So I'll write here from alcohols, ROH. Okay. Then we have studied that from alkanes. Okay, I'll draw from here alkanes. Okay. And the next one we have done is from alkenes. So I'll write alkenes here, and structure I can draw of alkenes like this. Okay. So I'll write here alcohols. So now remember from alcohols we have studied 6 methods of preparation. Okay. From alkenes we have 2 methods of preparation. From alkanes we have 1 method of preparation. Okay. So now what we are going to do? We are going to do all the 6 methods. So first I will do 6 arrows. Okay. So we can do like this, 1, then we have 2, then we have 3, and here 4, 5, okay, and one more we can do here, 6, okay. So the first one, okay, what is the first one we have done? First one is HCl and ZnCl2, that will give you RCl, okay. Next one, second one is NaBr and H2SO4. Remember, we have 6 methods, okay, 1, 2 done. The third one here is PCl3, sorry, PX3. So here I'll write, it is PX3, where X can be chlorine or bromine. Then the fourth one, okay, fourth one is P, we'll make little space here for fourth one, okay. Okay, so this is my fourth one. Fourth one is PX5, okay, or PCl5, sorry. So fourth one is PCl5, okay. Next, fifth one is X2 red phosphorus, right. Here X is equal to Br2 or I2, okay. So now sixth one will draw, okay. The sixth one is the most preferred one, okay. So sixth one is SOCl2, okay. So here I am writing it is the most preferred method. Clear? So you can see we have done all the 6 methods of preparation of alcohols, of haloalkanes from alcohols, right. Next, coming to alkanes. So alkanes, only one method is there, so that is your Cl2H nu, right. And this method is called as what? Free radical halogenation. So you remember, it is free radical halogenation, okay, fine. Now coming to from alkenes. So if you want to know from alkenes what is there, so from alkenes we have 2 methods. So I'll draw like this. 2 methods are there from alkenes. First is addition of HX. First is addition of HX. Addition of HX, right. Here what happens? Markovnikov rule is followed. Markovnikov rule is followed, okay. And this one is addition of X2, right. So that's done. We are done with the preparation of haloalkanes. See, so how many methods we have total? 6, 7, 8, 9, right. 9 methods of preparation of haloalkanes, okay. Fine. Let us now go to some question. So here one question is there. This is important, okay. Allylic bromination is carried out with. Now see, what is allylic bromination? As we have seen, suppose here this is there and I want to add a bromine in the allylic position, means here, right. So this is my allyl carbon, okay. If I want to add bromine in the allylic position, we need a reagent, that is NBS. The correct answer is option number D. Next, the reaction is known as, okay, one more method we left here. So sorry, we have left the halogen exchange method, right. So I'll add that here. Yeah. So we have halogen exchange method, okay. So here you have to remember, we have one is your Schwartz reaction, where one is Finkelstein reaction where we used NaI. This is Finkelstein reaction, and another one is your AgF we can use, where we can use Schwartz reaction, okay. So these 2 things also you need to add. So we have in halogen exchange method 2 methods, right. So total 6, 7, 8, 9, 10. So how many methods of preparations are there? So methods of preparations are 10, okay. So whenever you revise, you should recall these 10 methods of preparation, okay. Fine. Now coming to this one, reaction is also known as, so if you have Rx plus Ni, so this is preparation of iodoalkanes, it is your Finkelstein reaction, okay. Next, coming to preparation of haloarenes, okay, the aromatic ring. So here also we have 2 sources, one is from hydrocarbon, another is from amines, okay. So from hydrocarbons, what we take? Any hydrocarbon you take, any X2 you take, and you take Fe in dark. You can also use FeCl3 with instead of Fe in dark, okay. So this will, what it will do? It will add X in the ortho and para position, okay. Now we cannot get I2 here and we cannot get F here. Okay, fluorine is very reactive and I2 reactions are reversible. Okay, so that is why we can only get chlorine and bromine. Okay, so what should be X here? X should be equal to chlorine or bromine only. Okay, next is your Sandmeyer reaction. So you have to first take, this is your aniline. Okay, aniline means benzene with NH2 group. Treat it with Na, NO2 and HX. So we will get N2 plus and X minus. This is called as benzene diazonium chloride. Right, now if you treat it with Cu2X2, we will get X here, that is your and you can use chlorine or bromine, so you will get chlorobenzene or bromobenzene. Similarly, you can take Ki to get iodobenzene. Okay, so that was the reaction preparation of haloarenes. So let us draw the map for haloarenes map. So now I think all of you will be able to do with me. So we want to prepare haloarenes, right? So we have like this, I'll write Rx, ARX. Then we have from hydrocarbons, so we'll draw here. This one we can use a different color. Okay, so we have from hydrocarbons. Okay, and then next one we have from amines. Okay, from amines. Now if I see that from hydrocarbons, so I can write from hydrocarbons. Okay, and next one is from amines. Okay, so now if you see from hydrocarbons, what is there? From hydrocarbons, if we prepare, we will get and take X2 in Fe dark, right? And here if I take from this one, here first of all you need to convert it to this one, benzene diazonium chloride, right? So we can draw here. So first it will be converted to benzene diazonium chloride. Okay, that is N2 plus and X minus, right? So from here I can get, we can treat it with Cu2I2, where Cu2X2. Okay, so here we can treat it with, we will write it properly. We need little space here. So this one is like this and this one is like this. So we can use Cu2X2, okay, where X is equal to chlorine or bromine, and we can use Ki, okay, so to get iodobenzene. Okay, so this is the method of preparation. So here you can see 1, 2 and 3. So MOP for haloarenes is equal to 3. Okay, fine. So now a question here, compound A will be, so here that is your preparation from hydrocarbons of haloarenes. So here you can see that we have two, this H can also be replaced, this H can also be replaced. So the more stable, the H is replaced. So here it is a secondary one, this is more stable, so this one will be replaced. So correct answer will be option number B. Okay, next coming to physical properties. So first is your melting point. So if mass increases, melting point will decrease, if mass increases, melting point will increase, and if there is a branching, if the chain, there is not a linear chain, there is more branching is there, then the melting point will decrease. Okay, now coming to density. So the density increases with the increase in the number of carbon atoms, halogen atoms or atomic mass of the halogen atoms. Now coming to solubility. So solubility, it is less soluble in water, more soluble in organic solvent, and the solubility decreases with the increase in the mass. Okay, more mass is there, solubility will be less. Okay, so here a question is there, the arrangement of in the increasing order of their boiling points. So if you see, first one is bromomethane, that is CH3Br. Second one is bromoform, that is CHBr3. Next one is chloromethane, that is CH3Cl, and then there is dibromomethane. So now you see, first of all chlorine is there, its mass is less, so the least mass will be for chlorine. So third one will be least. Okay, so we can eliminate all other options. But let us check the answer. After that there is one bromine, so one will come, here 2 bromines and here 3 bromines. So correct answer will be option number C. Okay, fine. Now coming to, of the following alkyl halides, one with the lowest boiling point. So if you see, ethyl bromide is CCBr, I can draw like this, just the structure, skeletal structure. Then isopropyl bromide is like this, Okay, now if I see third one, N-butyl bromide, N-butyl bromide is like this, and then this one is methyl bromide. So if the mass is less, boiling point will be less. Here 2 carbon, 3 carbon, 4 carbon, 1 carbon. So mass is less here. So that is why option number D. Okay. Okay, next we'll come to part 3 where we are going to study about the chemical reactions. So first of all, we'll see chemical reactions of haloalkanes and haloarenes. So under haloalkanes, we have 3 types of reaction: nucleophilic, electroelimination, and reaction with metals. Now coming to haloarenes, we have nucleophilic reactions, electrophilic substitutions, and reactions with metals. Okay. So now coming to nucleophilic reactions, so we have different, one part will study what are the different nucleophiles, and then we'll see what is the types of nucleophilic reactions. So if you see what is the general mechanism of any nucleophilic reaction, we have Rx, okay, and we have Nu here, nucleophile, right? So nucleophile will attack on R and X will go out, so I'll get RNu. Right. So this is what is happening. So these are the different list of nucleophiles. Out of this, which are very, very important, we'll see NaOH, okay, aqueous NaOH or OH minus, H2O, NaI, NH3. Then if you see KCN, KCN will be the nucleophile is Cn, and if you take AgCN, the nucleophile is Nc. Okay, so this is very, very important. Similarly, if you take KNO2, then the nucleophile is ONO, and if you take AgNO2, the nucleophile is RNO2. Okay, then lithium aluminium hydride, nucleophile is H, we will get RH here, and here Rm plus, so this is your, we'll get, so here how it is, we'll get RR, alkane, nucleophile is R minus here. Okay. Now coming to types of nucleophilic reactions, so there are 2 types, SN1 and SN2. So what is the basic mechanism of SN1 and SN2? See, in SN1 what happens, suppose Rx is there, okay, first it breaks to give you R plus and X minus, okay, this is step number 1. In step number 2 what happens, R plus is attacked by the nucleophile to give you RNu, okay, and this is the slowest step, this is the fast step. This is the general method or steps of SN1. Now in SN2 what happens, SN2 if you see, Rx is there, okay, nucleophile will attack from the opposite side, so we will get Nu, then R, then X. This is a transition state, okay. Now after that we will get NuR, okay. So here a carbocation is generated, intermediate is formed, and here a transition state is formed. So we'll see quickly the differences between them. So first of all, it is a unimolecular reaction. So okay, let us write down the rate law also. So here R is equal to rate into concentration of Rx. But here rate will not only depend on the concentration of Rx, but also on the concentration of nucleophile. Okay. So now if we see the differences between them, first one is it is a unimolecular reaction, right? So there is only one molecule reacting, and this is a bimolecular reaction because here both Rx and Nu are reacting together. Next, SN1 follows first order kinetics. So if you see, the order is 1 here and here the order is 2. Okay. Next, mechanism of SN1 involves 2 steps we have just discussed, and here it is single step. Now if you see here, depends on the concentration of substrate only, rate only depends on Rx. Here it depends on both the substrate and the nucleophile. Okay, you can see in the rate law Rx and the nucleophile. Next, carbocation is formed here and no carbocation is formed here. Now there is no partial bond formed during, so there is no bond formation between the nucleophile and R. Partial bond is not formed, right? But here you can see a partial bond is formed. This is a partial bond that is formed. Okay. Next one, nucleophile attacks the carbocation from both sides. So once this carbocation is formed, okay, so carbocation is a planar molecule. So what can happen, the nucleophile can attack from both the sides, okay. So that is what is given here, and that will lead to a racemized product, okay. We'll get racemized product, means like dextrorotatory and levorotatory, both the products will form in small amount, okay, in this mixture. Now here attack of nucleophile takes only from the back side, so here we get only inverted product. So here nucleophile is always attacking from the backhand side, and we will always get the inverted product, right? So you see X was on this side, now Nu is on this side, that is the product has inverted, okay. Next, coming to, it is favored by mild nucleophile, this is favored by strong nucleophile. Now here for SN1 we require highly polar solvents, and here we require low polarity solvents. Next, here rearrangement can take place. Why? Because carbocation formation is there, and here there is no possibility of rearrangement. Now this is very important. The last point is the most important point, that is reactivity order. For SN1 it is 3 degree, 2 degree and then 1 degree. For SN2 it is 1 degree, 2 degree and 3 degree. This is from where questions have been asked repeatedly, this one and the solvent point. These 2 points many questions have been asked. Okay. Next one is your elimination reaction. So in elimination reaction, any base is present. So okay, the carbon which contains the X group is called as alpha, the adjacent carbon is called beta, and the beta H is abstracted, this bond shifts here and this X goes out and we get alkene. Right, so the product of elimination reactions are alkenes. Now in alkenes also we get, what is the rule here? In alkenes, more substituted alkene is formed as a product. More substituted alkene is formed. Now who says this? This is given by Saytzeff rule. Saytzeff rule. Okay. So you can example, if you see 2-bromopentane is there, there are 2 products possibility, that is pent 2Ne and pent 1ene. So more substituted means what? Near the double bond there should be more number of carbons. So near the double bond, here 1, here 1. So there are total 2 carbons, and here if you see near the double bond there is only 1 carbon directly attached. So this is your more substituted one. So here this is the major product. Okay. Fine. Now coming to reaction with metal. So reaction with metal, we have first one is your organometallic compound. So if we have any Rx and Mg, this Mg gets inserted into the Rx bond. Okay, and after this we can find CH3 CH2 MgBr, which is a Grignard reagent. And the second one is your Woods reaction. If you take Rx with Na, we will get RR, that is alkane, and NaX. Okay, so yes, that is there. Next, so next the question is which represents the aromatic substitution reaction. Okay, so aromatic reactions we will study little bit. Okay, after this we'll do this question. Okay, next let us solve this question. A compound whose molecules are superimposable on their mirror images even though they contain asymmetric carbon is. So this is a meso compound, right? If you see meso compound, they have chiral centers. Chiral centers means what? The carbon where 4 different groups are attached. So they have chiral centers, no doubt, but they mirror images are superimposable on each other. So that is why they are optically inactive. Okay. Next, optical isomers is exhibited by. So for optical isomers, what is the condition? There should be the presence of a chiral carbon. Now what do you mean by chiral carbon? 4 groups attached to the carbon should be different. Okay, so now what we can do, we can just draw the structures of this one. First one is primary butyl chloride. Okay, next one is secondary butyl chloride. Okay, secondary butyl chloride. The third one, if you see, tertiary butyl chloride. Okay, and the D option is isobutyl chloride. Okay, this is isobutyl chloride. Now if you see here, this carbon, 2 H groups are there, so all the 4 groups are not different. This is not answer. Here if you see, this carbon, this side methyl, this side ethyl, this side chlorine and this side hydrogen, all the 4 groups are different. So yes, this is optically active. Okay. Next, elimination of HBr from bromo to bromobutane. So if we have this one, 2-bromobutane, elimination can take place. So we can get 2 products here. One is your this one, okay, and another is this one. Now if you see around this double bond, there is 1 carbon only, and around this double bond there is 2 carbons, right? So which is more substituted? This is more substituted. So more substituted should be the major product according to the Saytzeff rule, right? So the correct answer for this one will be but2ene, option number B. Okay. Next, coming to the reactions of haloarenes. So under haloarenes, first of all, these haloarenes do not undergo nucleophilic reactions. What is the reason? Resonance effect, difference in the hybridization, that is carbon is sp2 hybridized, and the instability of phenyl cation. Okay. Now, but nucleophilic substitution, that doesn't mean it does not take place at all. It can take place under certain conditions. Okay. First, if you see, if you add NO2 group, Okay, so first of all, if you see this reaction, OH minus is the nucleophile here, it is reacting here and this is going out. So this is a nucleophilic reaction, but it takes at a very high temperature, 623 Kelvin and 300 atm. But now if you keep on adding some NO2 groups here, okay, so this temperature will be something around 400-500 Kelvin, okay. If you add NO2 groups, the reaction can take place even at the warmer condition. Now what is the reason for that? See, a nucleophile is attacking here, right? So that means the benzene ring or the haloarene should be more electrophilic in nature. Now how will it become electrophilic? If it has electron withdrawing groups, right? So now if you see, these all are electron withdrawing groups, these all are electron withdrawing groups. So these NO2 group makes the ring more electrophilic and hence the reaction with the nucleophile increases, okay. So what I can say here, the NO2 groups are electron withdrawing groups, right, and they decrease the density, they decrease the electron density on the ring and make the ring more electrophilic so that the nucleophile can attack on it easily, okay. And then you have electrophilic substitution reactions. So 5 major electrophilic substitution reaction. First is halogenation, addition of halogen. What is the reagent required for? Chlorine and FeCl3. Where will the halogen get attached? At ortho and para position, okay. Next one is nitration. For nitration, the reagent required is concentrated HNO3 and H2SO4. Here where the NO2 groups will be attached? At the ortho position and at the para position. Next, that is your sulfonation. You have to use concentrated H2SO4 and heat. Here where that is used? In the SO3H and SO3H, okay. Next, coming to Friedel-Crafts alkylation, CH3Cl-AlCl3. So here CH3 is attached and here CH3 is attached. Ortho and para alkylation takes place. Next we have CH3COCl-AlCl3. So that is Friedel-Crafts acylation. Again here it takes place at the ortho and the para position, right? Okay, so once again let us revise. There are 5 electrophilic substitution reaction. First one is halogenation. What is the reagent required for that? Chlorine in presence of FeCl3. Second one, nitration. What is the reagent required for that? Concentrated HNO3 and concentrated H2SO4. The third one is sulfonation. We have to use concentrated H2SO4 with heat. And the fourth one is alkylation. Here we can use Friedel-Crafts alkylation. The reagent required is CH3Cl-AlCl3. And then acylation, CH3COCl and then AlCl3. Okay. Fine. So now we'll question replacement of chlorine of chlorobenzene to give phenol requires drastic conditions, but chlorine of 2,4-dichlorobenzene 2,4-dinitrochlorobenzene is readily replaced. This is for what reason? So they are asking that chlorine from this one 2,4-dinitrochlorobenzene, the replacement of chlorine here is very easy. So just now we discussed, if we add NO2 group, what does it do? It withdraws the electron from the ortho and para position and make the ring electron deficient, right? And that is why if this is electron deficient, the nucleophile, the OH minus, right, it can easily attack here, okay, and this Cl minus can go out. So the first one, NO2 makes the ring electron rich. This is wrong. Withdraws from the meta position. No, NO2 is attached at the ortho and para position, so there is nothing to do with meta position. NO2 donates electron. No, NO2 is an electron withdrawing group. It will not donate. NO2 withdraws the electron from the ortho and para position. Okay, so that is the correct answer. Next, the structure of the major product formed in the following reaction. So here we have NaCN, right? NaCN minus is there. It is reacting with this one. So you have to remember, as I told you, this bond is very strong. Okay, in the aromatic ring, this bond is very strong, so this bond will not break. Okay, but this Cn minus can replace this chlorine. Here you see this one has replaced this one, so this is wrong. Here also this Cn will not attach to the ring, that is why this is wrong. Here also this is wrong, but here the Cn has replaced the alkyl chlorides, haloalkanes part. Okay, so correct answer for this question will be option number D. Okay, next, the following pairs of the halogen compounds which undergoes faster SN1 reaction. Okay, SN1, what is the degree? If you remember order, 3 degree, 2 degree and then 1 degree, right? 3 degree, 2 degree and then 1 degree. So here you see this is 3 degree, this is 2 degree. So out of these two, this one will react faster. So if you see this option is wrong, this option is wrong. Now out of these two, this is 2 degree, this is 1 degree. So yes, this compound will react faster. So this is wrong. This has to be the correct answer. Okay. Next, which of the following chlorohydrocarbon readily undergoes solvolysis? So you have to remember that for solvolysis, it is an SN1 mechanism. Okay, and SN1 mechanism depends on the stability of the carbocation. Stability of carbocation, right? So here if you see, this is a benzyl carbocation, this is primary carbocation, this is a vinyl carbocation, and this is a phenyl carbocation, right? The benzyl carbocations are very stable due to resonance. So here what I can see, the bonds will be like this. So this can resonate and can stabilize this carbocation. So more is the stability of carbocation, higher will be the rate of the reaction for SN1. So the correct answer here will be option number A. Okay. Okay, so yes, so students, this was a one-shot video on your haloalkanes and haloarenes. We have done a detailed lecture, but here I have revised all the reactions that is required, starting from the preparation of haloalkanes, reactions of haloalkanes, preparation of haloarenes, and the reaction of haloarenes. Okay, so I want all of you to draw this mind maps and study reactions, because this is the first chapter. Once we are doing more chapters, the number of reactions will increase. Okay, so please take a one A4 sheet paper. On the top of that, so you have to divide it like this. So if I tell you, what I want you people to do is take two A4 sheets paper, one A4 sheet paper. Okay, so on this, divide it like this. Okay, here it is methods of preparation of haloalkanes, and here reactions of haloalkanes. Okay, and backside of this paper you have to take methods of preparation of haloarenes and reactions of haloarenes. So the entire reaction of this chapter will be in one particular page, and that will help you to revise so fast. Okay, so yes, I hope this video was helpful to revise everything and to practice some questions also. So yes, if you are finding this series useful, if you are finding this series can help you to achieve your 60 out of 60 score, then do not forget to subscribe the channel. Okay, and also please join our WhatsApp channel. The link of these PDF of these notes and everything, the question paper solutions will be available in our WhatsApp channel. Okay, so do not forget to join, and all the very best for your KCET 2025 preparation. See you soon in the next class.